Okay, what's up, everybody? Today we are 10.2. We are going to introduce you to a geometric series and something known as a telescoping series. Let's go ahead, let's get started. All right, so a series, an infinite series, the sum of an infinite sequence, a sub n, is called an infinite series, okay, the sum. Okay, so when you take a infinite sequence and you add up all of its terms, you get what's known as a series, okay? We represent a series using summation notation. This is our uppercase sigma, and that is the symbol that actually is for sum, S-U-M. Okay, so just know that right here, that a sub n, just remember that that is our rule of sequence. Rule of sequence. Try not to get the words series and sequence mixed up. Series is a string of numbers separated by commas, and you can write a rule for it. A series, okay, is that sequence, but with plus signs in between the terms to show that we want to add each term of that sequence together, okay? If the sum approaches a finite value, okay, if the sum approaches a finite value, then the series converges. Otherwise, it diverges, okay? Now, uh, next thing that we're going to talk about is something called a partial sum. A partial sum is the sum of the first n terms, okay, of a series is called the nth partial sum. Usually when we try to get to some n value and it's not infinity, that's why we call it a partial sum. An infinite sum, that top value on sigma would be an infinity sign, where here it's going to be an n. All right, so in this case, we're going to add up, if they want S sub 4, like this value right there, that subscript, like if that was a 4, then they would want the sum of the first 4 terms, okay? If there was a 7, then they want the sum of the first 7 terms. We can utilize the concept of a partial sum to help us determine whether or not an infinite sum will actually converge or diverge. Let's take a look at our first example. All right, so we're going to consider that series right there. It's an infinite series. It says n starts at 1 and goes to infinity, and then the rule of sequence is 1 over 2 to the n power. All right, so the first thing that we're going to do is I'm actually going to explore the concept of rewriting that. It's a pretty powerful tool. Watch as I go ahead and just kind of rewrite this. You're going to have to excuse my sigma notations because I'm just going to forewarn you as this lesson goes by, they are going to get worse and worse as it goes along. It may start off pretty good. Okay, that's not a bad one, but they're just going to get yuckier as we go. Now, I'm actually going to rewrite 1 over 2 to the n power as 1/2 raised to the n, because technically it's the same thing. Now, what we're going to do is we're going to list out the first 4 partial sums, okay? That's part A here. So they want S sub 1, which says, let's find the first term, okay? And as a matter of fact, what I am going to do is I'm going to find the first 4 terms of the sequence. So if I just find the first 4 terms of the sequence, that would be n starting at 1 would be 1/2, and then 1/4, and then 1/8, and then 1/16. Those are the first 4 terms, okay, of the sequence. Now let's find the first 4 partial sums. So I'm going to take S sub 1, okay, and what I'm going to do is that's the sum of the first term. Well, that would be 1/2. And then I'm going to find S sub 2. Now S sub 2 would be the sum of the first 2 terms. Well, all that means is if I take the sum of the first term and then add in the second term, that should give me the sum of the first 2 terms. So that's going to be 3/4. And now I'm going to find S sub 3. S sub 3 is the sum of the first 3 terms. Well, I can just take S sub 2, which would be the sum of the first 2 terms, and then add in the third term, and that would give me the sum of the first 3 terms, and that would be 7/8. And then here, S sub 4, okay, notice that this is S sub 1, sum of the first term. This is the sum of the first 2 terms. This is the sum of the first 3 terms. Now we're going to go S sub 4, which is the sum of the first 4 terms. So legitimately, if I just take the sum of the first 3 terms and then add in the 4th term, should give me that, and that should give me 15/16. Now, what we're going to do is now I've listed out the first four partial sums for my first four partial sums are 1/2, okay, 3/4, 7/8, 15/16. Okay. Let's take a look at part B. It says write out a formula to represent S sub n. All right. Well, S sub n in our case is going to be 1/2, comma 3/4, comma 7/8, comma 15/16. All right. So you know what? That is just terrible looking. I'm just going to go back and redo that. Okay. So let's go S sub n is equal to 1/2, comma 3/4, comma 7/8, comma 15/16. Now, these sums actually formulate a new sequence, okay? So let me say that again. These sums actually give me a new sequence. This sequence can actually help me determine whether or not the infinite series converges or diverges. All right. So we're going to write out a formula to represent S sub n. So I think S sub n is actually equal to, looks like I'm going to go 2 to the n minus 1 over 2 to the n. Okay, so that way if I start plugging in values for n, you should notice if I start plugging in 1 and then 2 and then 3, and then you can see that that is actually going to give me the sequence formulated by the sums. I would recommend pausing the video and just taking a look at what I've got right now and just determining whether or not that makes sense to you, how I got that, okay? All right, so let's go on to part C now. Okay, part C looks like we are looking at here. Determine if the sequence S sub n, which I just wrote up above, converges or diverges. All right, well, I think what we're going to do is I'm going to, because I can't really make that justification yet because I got an exponential minus some constant in the numerator over some exponential. Well, let's just take a look at something really quick. So let's say that I've got the limit as n approaches infinity, okay, of 2 to the n minus 1 over 2 to the n. These partial sums, again, are going to help me determine whether or not the infinite series converges. So what do? Well, let me go ahead and break this apart using those limit properties that I know so well. 2 to the n over 2 to the n minus 1 over 2 to the n. Okay, well, I can see that this part right here, that's equivalent to the number 1, because anything divided by itself is always just 1. Okay, and then I know that over here, this is a constant, and this is a exponential, and I know a exponential grows faster than a constant, so therefore this is actually going to be 1 minus 0, which is 1. So I can say that the partial sums actually converge to 1. Okay, my formula converges to 1. All right, so therefore, since that thing converges, let's take a look at our next step. It says, for an infinite series, okay, the nth partial sum is denoted by this thing, which we just did, okay? If the sequence of partial sums converges to S, which we just saw converges to S, okay, then the series, that infinite series, converges, okay, also converges. Now, the limit S is called the sum of the series, okay? It's called the sum of the series. So basically what we did is we actually utilized that partial sum to help us figure out what the infinite series would either converge or possibly diverge to. So again, our partial sum, our nth partial sum converged to 1, so therefore our infinite series should, letter D, converge to 1, okay? And again, if your S sub n, which we just found over here, diverges, then we know the series diverges. All right. So hopefully you are getting that. Hopefully that makes sense. And again, definitions of convergent and divergent series. So if you have, again, if you have an nth partial sum and that partial sum converges to some value, we'll call it S, then the infinite series converges, okay, to that same value. All right. Okay, so I think what we're going to do is, I think I'm actually going to stop the video there. I'm going to call that part 1, and then we will have a part 2. All right, Mr. Miller is out.